Hello everyone, my name is Daria. I am a PhD student at the Scopus Institute of Science and Technology, and today I am pleased to present you our research, exploring the role of electrotactile and kinesthetic feedback in telemanipulation tasks. Nowadays, more and more systems are being switched to autonomous or remote control operations for various reasons, such as the convenience of monitoring from anywhere globally, restrictions related to the epidemiological situation, and the mobility of systems. The current situation with coronavirus has shown that the critical medical systems used for testing for the presence of the virus exist only in manual collection and processing of PCR tests, which can be dangerous for medical staff. Therefore, there is a demand for a robotic system capable of handling soft and fragile objects, such as laboratory equipment, with high precision, which is the focus of our research. A dexterous telemanipulation can be achieved by providing the operator with multimodal high-fidelity haptic feedback. The use of effective combinations of haptic stimuli is currently the subject of active study by many research groups. In this work, we propose a robotic telemanipulation system with a multimodal haptic feedback system that combines kinesthetic and electrotactile stimuli for precise remote dosing of liquids. The proposed system consists of a robotic manipulator with 6 degrees of freedom equipped with a 2-finger gripper and high-fidelity tactile sensors mounted on the gripper. The operator controls the robot using the Omega-7 desktop haptic device with 2 embedded electrotactile displays on the handle. As a visual feedback channel for the operator, we use a hybrid environment composing real-time video streams accompanied by a digital twin of the robot. The high-density tactile sensors scan the contact surface, measuring the internal force and pressure applied to the grasped objects during the manipulation process. The obtained information is transmitted to the operator in the form of haptic feedback. The user is provided with both kinesthetic and tactile feedback. As a result, the operator can feel both the grasping force applied to the object by a robotic gripper and the detailed information about the force distribution, which is the applied pressure at the contact surfaces represented by electrotactile patterns. To evaluate the proposed telemanipulation system, we elaborated a 2-stage experimental scenario for dispensing liquid with a plastic pipette. At the first stage, we investigated the role of each haptic feedback channel for the proposed system during the liquid dispensing operation with a semi-autonomous teleoperation system, where the position of the robot were predefined. The haptic feedback provided to the user was presented with 3 methods of contact force rendering, namely grasping force simulation with Omega-7 haptic device, distributed force simulation with the electrotactile display, and a combination of the both methods. 2 metrics were chosen as the main parameters affecting the teleoperation efficiency, namely accuracy of liquid dosing and time of dosing operation. The experimental results revealed that the mean dosing error in the case of multimodal haptic feedback decreased by 66% relatively to visual feedback mode. In terms of liquid dosing time, the tasks with electrotactile and multimodal haptic feedback were performed the most efficiently. The task was completed 20% faster for visual plus electrotactile feedback and 18% faster for multimodal haptic feedback compared to pure visual feedback. At the second stage, the experimental task was to perform a liquid dosing operation using the developed system with multimodal haptic feedback in the full teleoperation mode. For each participant, we measured task execution time and the accuracy of liquid dosing. In addition, after completing the task, We asked participants to evaluate the system with an NASA TLX questionnaire using a 7-point Likert scale. In terms of liquid dosing accuracy, participants showed comparable results to the first experiment with semi-autonomous control. The average amount of dispensed liquid was 2.07 milliliters. The mean absolute error comprised about 9% of the required volume of 2 milliliters. Overall, the participants highly assessed their performance with a low level of frustration during the task. Besides, the task execution through a developed system did not require special mental and physical costs, as well as putting a lot of effort from the users. In this study, we evaluated the effect of multimodal haptic feedback for the developed telemanipulation system during liquid dispensing operation. The experimental results showed that the proposed approach to use a combination of haptic channels allowed operators to increase accuracy and decrease time of liquid dosing task compared to pure visual feedback mode. Overall, users demonstrated better performance using a multimodal haptic feedback system than when using each haptic channel separately in combination with visual feedback. The proposed technology can be potentially implemented in delicate dosing procedures during the antibody tests for coronavirus, chemical experiments, operation with organic materials, and telesurgery. In future work, we are going to use deep learning techniques for the development of the perception system, allowing to recognize the properties of the grasped object. In addition, we will conduct experiments with a larger number of objects that differ in softness, shape, and texture. Thank you for your attention. For more information, please refer to the paper. If you have any questions, feel free to contact us via the provided email.